The final step in writing our computer program is to evaluate the remainder constant after we do the division of the polynomials. And if you recall, the formula that we had developed for computing this remainder is shown right here in this expression on the top in green, right here, this expression, okay? And you see that it also has the appearance of being a type of a recursion relation insofar as we compute this value and then we compute, so imagine here's what I'm going to do. I'm going to call this value right in here, B0 divided by B1 times A4. Suppose I call that, that's my first estimate for, for the remainder. I'm going to call that, let's say, R equals B0 divided by B1 divided by A4. Now I'm trying to get the general formula for the expression and not the one that just only works for fourth order polynomials where the largest coefficient is A4. In general, if I'm dealing with an nth order polynomial, okay, so an nth order, the largest coefficient is going to be an. So I'm going to assume here that this formula that I have developed in fact works for higher order polynomials. So where A4 appears right here, in my computer program, I'm going to put an. Remember that n is the order of the polynomial, the original polynomial, because A4, A3, A2, A1, the a's are the coefficients of my original polynomial, p sub n of x. Now I've already computed the value for q, the quotient polynomial, which is an order of 1 degree less than p sub n. Why did I write n minus 3? It's not, it's order n minus 1. Sometimes I'm thinking things and my hand doesn't write what I'm thinking. Okay, so q sub n minus 1. Okay, now, so we've already figured out how to compute that. So now I want to compute this remainder term. So what I'm going to do is now, instead of using a sub 4 explicitly, I'm going to use a sub n. I'm going to take as my first estimated value for r, b sub 0 divided by b1 times a sub n. So that would be my first r. Then my second r is going to be this calculation of this term right in here, okay, this term. And this is going to be b sub 0 divided by b1 times a sub n minus 1, because here we see that 3 is one integer lower than 4. So a sub n minus 1, and then minus my previous estimate for r, which was this term right here. So I have minus r. Okay, remember r is the first estimate for r was this, so this is minus r. Then my next estimate for r is exactly the same form. Here I take b0 divided by b1, b0 divided by b1 times a n minus 2, that's what this is, a n minus 2, minus this whole term, which was the estimate for r that I just calculated right here. And we keep going on using this pattern of calculations over and over again. Now, when we get to the very end, the last term, the last estimate for r is different, because the last estimate for r is just simply a0 minus the previous estimate. We don't multiply by this term, the b0 divided by b1, for this last estimate. So we want to write our program that implements, first computes this estimate for r, then we're going to go through a for loop to do all these, and then after the for loop is over, we're going to compute this. And this is exactly what this set of basic programming statements does. Notice I begin with a remark, now to compute the remainder. So I find my first value, my first estimate for R, which is this term right in here. It's B0 times AN divided by B1. Okay, so that's my first estimate for R. Then I go into my for loop. My for loop runs from here all the way down to here. Okay, my for loop, I go from I equals 1 to n minus 1. Remember that nm1 was a variable that I previously defined to be n minus 1. Now I do something that should be familiar to you right here. I generate this variable I call I backward. I backward is nm plus 1 minus I. So for example, when I equals 1, I backward is equal to n minus 1. When I is equal to 2, I backward is equal to n minus 1 minus 2. So I now execute this command over and over again, which is, it looks like this statement right in here. Okay, it's B0 divided by B1 times A of I backward minus R. And like I said, when I is equal to 1, this is just equal to n minus 1, which is exactly what we want here. So it does, this executes then, when I equals 1, it gives me my second estimate for R. Okay, then it goes back up, implements everything again. This time I backward is n minus 2. So that's this right here, and it calculates B0 divided by B1 times A n minus 2 minus R. So we execute this all the way up until the point when I is equal to nm1 or I backward is equal to 1. So the last calculation that it does is when the A1 term appears right here. So it executes the loop, successively computing these estimates, these recurring or recursive estimates for R. But like I said, the last one is different. So we compute that one outside the loop after we have finished executing this. So we come down here, and outside the loop, I compute this final estimate for R, which is just simply A0 minus the previous estimate for R. In other words, A0 minus R, that's what this is. R is equal to A0 minus R. And at this point, I should, if everything is done correctly, have successfully computed the remainder R.